So now let me see. We have a lab tomorrow at 2, right?
2:30, 2:15.
You can be late. Your partner will cover for you. Yeah. But anyway, I was just overhearing you guys. It sounds like some people didn't realize that for the
Industry?
the numbering is, it's 0, 1, 2, 3 on the first row, 4, 5, 6, 7 on the second row, and some people forgot to do 8, 9, 10, 11 on the bottom row, and therefore everything's all wrong. So anyway, if you want, you can hand it in tomorrow in the lab. You can have an extra day if you want. Okay, so if you made that mistake and you don't want to hand it in today, that's fine.
Does this correction ink, is that too bad, or is it legible? It should be pretty legible.
Yeah, I think I can see that. But now make sure that I can see the
circles,
the grouping, of all the key maps. So are there any questions about the homework other than maybe this one, this little problem? Okay, so what we have started to do in class last time is we started talking about practical circuits. And the first practical circuit that we looked at was the multiplexer. And how do we remember what a multiplexer does? What was our little mnemonic device? Multiplexer M, many to one. Okay? So a multiplexer selects one of several data inputs to be routed to a single data output. And here in figure 10.43 is an 8-input multiplexer with 3 select lines. Does everybody remember how that works? I mean, what that does? Any questions about that? And here on figure 10.44 we saw the implementation. And then the next device that we looked at was a binary decoder. And a decoder takes a binary number as input and sets one of the data output lines to 1 and the rest to 0. All right? So here was an example of a 4-output binary decoder. So it takes a 2-bit number, S1, S0, and if S1, and we consider here in the truth table on figure 10.45, we see that if S1, S0 is if we think of it as being a decimal number, so its value can either be 0, 1, 2, or 3, then if it's 0, then D0 is 1 and the rest are zeros. If it's 2, then if it's 1, then D1 is 1 and the rest are zeros. If it's 2, D2 is 0 and the rest are zeros. And if it's 3, D3 is 0 and the rest are zeros. Yeah? Is everybody with me? And then here's an abbreviated diagram. We need 4 separate circuits, but each one is a simple AND gate. And this is the abbreviated. You could always fill in the non-abbreviated, could you not? All right. And we said in figure 10.47, we said that we can actually stick an enable gate here. And I think we discussed briefly about how to make the enable gate, how to implement the enable function on this chip, right? Because, and what does enable do? If enable is 0, then what does that do?
It makes it so that every output is 0.
Every output is 0 regardless. And then if enable is 1, then it functions as it is supposed to function. So turning it off is equivalent to making all the outputs 0. We don't physically turn the power off. Yeah.
So doesn't that the enable wire would go to each of the AND gates at the end?
It would. Actually, let's go back and discuss the implementation. Yes, it would. Yes, it would fan out. Right. So there would be one enable line, and that enable line would go into each one. So these would be 3 in figure 10.46. Instead of being 2 input ANDs, they would be 3 input ANDs, and one of the lines would be the enable would go to each one of those. So if enable is 0, nothing would get through any of them. That's good. Does everybody see how that? Does everybody see how that works? All right. Now, well, if we had, did we do the demultiplexer now? I don't remember. Is that what we were going to start? Okay,
Yeah,
good. Okay. So now, if there is a multiplexer, then there must be a demultiplexer. Well, if a multiplexer is many to one, a demultiplexer is one to many. So here, let's see how that would work. So let's have a, let's suppose we have 3 selects here. Okay, so this would be S2, S1, S0, and we would have, let me see, demultiplexer. 1 coming in, and 1, 2, 3, 4, 5, 6, 7, 8. Are you with me? And this would be, these are coming out, and so this would be D0, D1, D2, D3, D4, D5, D6, and D7. And this is coming in, so we'll call this D for data. And if this S2, S1, S0, if this were 0, 1, 1,
It would go to 3, D3,
yeah, this D would be routed
in the black box.
in the black box to here. And what would come out here would be D, and what would come out here would all be what? What would come out here?
Nothing. 0.
Well,
0.
Yeah.
They'd all come out 0.
Yeah, these would be zeros, not nothing but 0. 0 is something. Is there, well, it would depend on what D is. If D is 1, then this would be 1. If D is 0, then this would be 0. Are you with me? Yeah, that was a good question. Does everybody see how that works? Okay. So a demultiplexer routes a single input value to one of several output lines, and the control lines determine the data output line to which the input gets routed. And here's a picture of a smaller one, figure 10.48. Here we have a 4-output demultiplexer, and so it only has 2 select bits, S1 and S0. And here is the truth table for this, right? Wait a minute. This says if S1, S0, 0, 0, there's a D here. If it's S1, S0 is 1, 0, 1, there's a D here. 1, 0, there's a D here. 1, 1, there's a D here. Does this little pattern ring a bell?
It's like a binary decoder.
It looks kind of like a binary decoder, doesn't it? As a matter of fact, what? As a matter of fact, what?
It is binary.
It is, but what kind of a binary decoder? A binary decoder with, it is a binary decoder, but what kind of a binary decoder? It's a binary decoder with what?
Like an exclusive OR?
No.
An enabler on it.
With an enable, actually, think about it. If
D is 0,
D is 0,
it'll turn everything to 0.
everything should be 0,
disabled.
which would be like as if it's disabled. And if D is 1, then what?
It'll act normally.
It will act normally. So actually, does everybody understand what we just discovered? A demultiplexer is actually the exact same chip, does the exact same function as a what? As what?
Binary.
This binary decoder with an enable. The only difference is in figure 10.47, the enable is down here and the S1 and S0 are here. And in figure 10.48, we just put the enable line here and we call it D instead of enable. And we put the S1 and S0 here and it does this binary decoder. I mean, it does a demultiplexer. It's the exact same implementation. There's no separate chip. You see what I mean? Is everybody with me on this? It's just a viewpoint, another little viewpoint. Same way that it's the same way of thinking, oh wait, what is a selective inverter? It's just a little different viewpoint. What is a selective inverter? What did we find was a selective inverter?
Like an OR and AND gate?
What was it? What was the selective inverter? What is the chip? What is the gate so that if it's 1, we invert it, and if it's 0, we don't invert it. It just goes straight through. What gate does that? Oh, we just, exclusive OR. Do you remember that? And what is an enable gate?
An exclusive one.
No, and enable. I mean, what either sends it through or doesn't? What gate?
The enable gate?
And gate.
AND gate. The AND gate. We just treat one of the inputs as an enable, and it will either pass it through or not. Do you remember this? I think this was from, is this from last time, I think? Okay, good. A little review. All right. So now, are there any questions about this, about any of this so far? All right. Now, the next thing we're going to do is we're going to do addition. Not only, okay, we're going to do addition and subtraction. All right, we're going to see how addition works. All right. So now here's the thing. We know how to add, you know from computer systems how to add in binary, right? Let's remember how to do that. Let's take a 4-bit number. Let's say 1101010101. And let's add. Now, do you remember how to add in binary?
Kind of.
Okay, so how do we do it? 1 plus 1 is what?
1.
Is 0,
Carry the 1.
carry the 1. Now, do you guys remember that? 0, carry the 1. And then 1 plus 0 is what?
1.
1, carry the what? 0. 0 plus 1 is
0.
0, carry the 1. 1 plus 0 is
0.
0. And then what did we have out here? We had the C bit. The carry bit is 1. You remember how that worked? Okay. And the other thing that we had was the overflow bit. Do you remember how the overflow bit worked? What would V be, in this particular case, what would the overflow bit, if this were a 4-bit number? What kind of a number, if we consider this to be a signed number, what kind of a number is it? Positive or, I mean, is it negative or non-negative?
Negative number.
It's a negative number. What kind of number is this?
Positive.
Can you ever have an overflow when you add a negative number and a positive?
No.
So therefore, the V bit in this case would be what?
0.
0. Does everybody see how that works?
What about N and Z?
Yeah, and would just be a copy. Yeah, we'll get to that later. Actually, we will see in detail how that works later. But let's postpone that. The question was, what about the N bit and the Z bit? Okay, now here's what we're going to do. We need a circuit. What we need is, we don't have addition. We don't have an addition circuit. All we have is ands and ors, nands, nors, XORs, whatever, you know. So we need to have our circuit do arithmetic. So what we have to do is we have to use our gates, use the gates that we know and how they work to actually perform arithmetic, addition. Now here's the thing. This addition right here, this addition here is performed with what's called a half adder. Okay, this is performed with a half adder. A-D-D-E-R. So this, the first one on the rightmost side, that's performed with a half adder. And so how many inputs does the half adder, actually I should do it like this. Now, so how many inputs does a half adder have? 2 inputs. And how many outputs does it have? 2. Is everybody with me on that? See, it needs two, it has two inputs for the, oh, and by the way, this is just one column. The half adder is just for one column of addition. It's for the rightmost column of the addition. Are you with me on this? So it has two inputs. We're going to call them A and B.
Okay.
All right? And then it has to output both the sum and then the carry that goes over to the next column. Are you with me? Now, so that's a half adder, and that's appropriate for the rightmost column. But what do we have to do for the other remaining columns? In other words, what did we do here? We did 0 plus 1 plus 1, and we got 0, and we did what? A carry of 1. So this computation here is done with what we call a full adder. Okay, so this is performed with a full adder. All right, now let's think about our inputs then. Performed with a half adder, so with this one, how many in, how many out?
3 in.
No,
this one's
the
2
half
in, 2 out.
adder. So this is 2 in, and then what out? 2 out. Does everybody see what they are? The 2 inputs are the bits to be added. The 2 outputs are the sum and the carry. And this is performed with the full adder, but now how many inputs does a full adder have?
3.
It has 3 in, and how many out?
2 out.
2 out. And these are all combinational circuits, which means what? Combination. The output depends only on the input. But we know what those should be, right? From our rules with addition. So this is 3 in. 3 in, 2 out. Are you with me? All right, you guys. So the half adder. The half adder adds the rightmost 2 bits of a binary number. The inputs are the 2 bits and the outputs are the sum bit and the carry bit. Now, let me ask you what we're going to do is let's do a truth table. And let's see if we can specify what the circuit should do. So let's have I'm going to call it A, B will be the input. This is not a good pen. I never make the A, B, and then we're going to call this sum and carry. Okay, so AB is 0, 0, 0, 1, 1, 0, 1, 1. So knowing, here, can you specify this? Do this, fill out what the sum and the carry should be on this truth table. A and B are input. Sum and carry should be what? Can you do this in your notes? Can we do this? Okay, so what'd you get? What do you have? What do you have for us?
So it's 0,
Let's go down.
Oh, 1.
0.
1, 1, 0.
Is everybody clear on that? Why that is? And what about here?
0, 0, 0, 1.
Now I ask you,
What are they?
yeah,
The first one is exclusive OR.
exactly. This is the exclusive OR. And what's this one?
That is the AND.
And. Ha!
Which is the same thing as enable and invert.
Well, yeah, it's and. Yeah, okay? So look, figure 10.49, you did it. Good. See, here's the truth table. By the way, here's the block diagram. So now normally we have, okay, there's this convention that we normally do in logic design, and that is that the signals normally flow from, either they flow from left to right, or sometimes we draw them so that the inputs come from the left and the outputs go to the right, or we have the inputs come from the top and we have the outputs go down to the bottom. But it's more convenient, it's much more convenient, however, or it's less confusing when we do adders to have, you know, the output of this has to go to the input of this, and the output of this has to go to the input of this. So we normally have the outputs going to the left because that's the way we add. Do you see what I mean? So notice in this block diagram that we have the input A and B is coming from the top, and then the sum is coming out to the bottom, and then the carry is going to the left. And then why is the carry going to the left? Because this carry 1 is going to go, there's going to be another circuit over here, and that's going to be the input of the next full adder. Are you with me on that? So here it is, the sum is 0, 1, 1, 0, the carry is 0, 0, 0, 1, so the sum is the exclusive OR. And so look, here's the implementation. An AND gate and an XOR gate. There's your half adder. Now we can do arithmetic. And now, what about a full adder? Now what would I have? What would we have to have for the full adder?
ABC, 3 inputs.
A, B, C, and now what we call it is carry in.
Oh, carry in. So C would be carry in.
Well, we have now with the full adder we distinguish between carry in and carry out.
Right.
So we have a C in and a C out. That's the common way to denote it. Is everybody with me? So here let's talk about the full adder. The full adder adds one column of a binary number. The inputs are the 2 bits for that column and the carry bit from the previous column. And the outputs are the sum bit and the carry bit for the next column. All right, so now let's do that. Now you should be able to do this. Let's see. So the block diagram would look like what? It would be here. It would be A and B, and then this is the sum. I think we're going to call, yeah, we're going to call this sum. And now, because the carry propagates to the left, we're going to have C. So this is, we're going to call this C in, and then we'll call this one C out. So now does everybody agree that this is what the block diagram of a full adder should look like?
Sure.
Are we good? Is this all very logical? Okay. And now let's do A, B, C in. Let's do A, B, C in. And let's do sum and C out. All right, you guys, get your pencils out and on your notes.
0, 0, 0.
Yes, let's do it. You do it yourself. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. All right, so here's the table. And let's take a minute and you fill out the table. And we'll see if you can get it. No fair peeking on the next slide. That goes for you guys too out there. Huh? We'll go around the room. So. All right. Okay, are we done? Is everybody, are we good? Okay, so where should we, we're going to start in the middle row. Okay, Shane over there in that side of the middle row. And I'll tell you what let's do. Let's just take the sum column and we'll go down, and then we'll take the C out column and we'll go down. Okay, so you just tell me one bit. Just tell me. So what is this?
0.
0. Next? 1. 1. 0. Man? 1. 0. Camera operator is in on this. 0. Oh, sorry. You want to pass? Oh, you want 0? Okay. Ben?
0.
0. 0. Shane? 0. 1. 0. 1. 1. 1. Does everybody agree?
No.
Oh, we have some disagreement. Okay, we won't say who. How many disagreements? Here.
Bottom of sum.
The sum on the bottom. This should be what? 1? Because if you add 1 plus 1 plus 1, the sum is 1 and the carry is 1. Yeah, you're right. So let's see if the rest of them right. Let's check it with figure 10.50 now. So there's our block diagram in part A. So 0, 1, 1, 0, 0, wait, 0, 1, 1, 0, 1, 0, 0, 1, and then 0, 0, 0, 1, 0, 1, 1, 1. All right. Now, here's the thing, you guys. One way to do this would be to, actually I think I have an exercise for you to do a Carnot map on these and have it be 2-level. Were you just talking about that?
That's what he wanted to do in the first place.
And that's what you want to do, yeah. Well, I mean, but you could. But you'd be 2 Carnot maps, one for the sum and one for the C out.
Right.
And it could be 2-level. But we can use, there's another way to do it. Why do you suppose we called, albeit maybe not quite so efficiently, but why do you suppose we call it a half adder? And how can you make a full adder? You can make a full adder out of what?
2 half adders.
2 half adders, because actually, what are you doing? You take the sum of the 2 bits, right? Mm-hmm. And then you take the sum, and you take the sum of those 2 bits, and you do what?
Add the carry.
You add the carry to that.
Right.
Are you with me? Does everybody see how that would work? So here, in figure 10.51 is a block diagram of how to make a full adder out of 2 half adders. Does everybody see how this works? So look, what we have coming out at the top, we add A and B. Okay? So now here, by the way, you guys, we're going to have, we're going to label the inputs of the half adder as A, B, C, and S. Does everybody see how that works? The A and the B are the 2 inputs. The C is the carry out, or is the carry of the half adder, and the S is the sum of the half adder. But then the labels on the outside don't necessarily match. Are you with me? So this top half adder, we have A and B being added, and then the sum of that half adder goes to the sum output of the top half adder goes to the A input of the bottom half adder. And then the C in goes to the B of the bottom half adder. So we add these 2 bits, and then we add the carry to we add the sum to the carry, and then that sum comes out. Yeah, question?
If you had 1 on both of the C outs, how come you don't lose 1 after you OR them?
That's a really good question. We have to make sure that this C out with the OR gate being the OR of these 2 C's is correct. Can you convince yourself why that is correct? Are you going through all the combinations to try to figure out why that is correct? See, the question is, what about this computation for C out here? Why is that correct? If you have, okay, look, do you agree that if you have a carry in the very, do you agree that if you have a carry of A and B, you've got to have a carry for the total? Right? Regardless of what the carry in is. On the other hand, if you don't have a carry for that, but you have a carry because of the third addition, you also have to have a carry. So, but it's okay to have the carry for both. In that case, you just have the carry. That's when you're adding 1 plus 1 plus 1. Did that last one? Okay, look. Suppose A and B are 1, 0. Then the carry of the top one is 0. But if the carry in is 1, then the sum and the carry in will be 1, and there will be a carry out of the bottom half adder, and the carry will be 1. So you could either have the, are you with me? But on the other hand, suppose you're adding 1 and 1, suppose A and B are 1 and 1, in that case the carry out of the top adder is 1. And now, it doesn't matter whether the carry in is another 1 or the carry in is another 0. If the carry in is another 1, then there will be a carry out from the bottom adder, half adder, and it will be 1.
Wait, is that because the C out can't be 1 in both of those? Because you can only have up to 3 1s, so you can only send the carry over once.
Actually, maybe what we should do is look at this truth table. Check, oh, this is what we should have done in the first place. Well, no, because this truth table doesn't have the carries of the intermediate, we don't have a column here for the carry of each half adder.
Yeah.
But if you look at this truth table in figure 10.50b, you can see that whenever if A and B is 1, if A and B are both 1, it's 1 regardless of what C in is. Does that help?
Yeah, I think I understand it now. I'm pretty sure.
Okay, are we good? Okay, so now you guys, how do we actually, this is just one column. So now how do we add like a 4-bit number?
So you'd have the half adder on the far right.
Far right, half adder on the far right.
In this image, if you look at figure 10.51,
Yes.
where the C in is coming out is just another half adder.
Well, it would just be a half adder for the right column.
Right. So that'd be your half adder.
Yeah.
And then you'd have 3 more of these.
Three more of these full adders.
Right.
That's right. So, and that is called, now, does everybody see then, what would happen is, it'd add the first, and then the output would go to the input of the next one, and then that would go to the input of the next one. And so it would be like a ripple it would be like in a pond when you throw a stone into the pond,
So you can just loop
and it ripples out. So this is called a ripple carry adder. A ripple carry adder adds 2 n-bit binary numbers, and the inputs are the 2 n-bit binary numbers to be added, and the output is the n-bit sum, the c bit for the carryout, and the v bit for the signed integer overflow. All right? So here it is. Are you ready for this? Drum roll. Here it is. So in figure 10.52a, we have the block diagram, and if we're adding 2 4-bit numbers, we have A3, A2, A1, A0 for the first number, and B3, B2, B1, B0 for the second number. Is everybody good? And then we have S3, S2, S1, S0 for the sum. And then we have C out and V coming out for this 4 bits. And what is inside of that? Here's the implementation for part B. Notice we have block diagram, implementation. Now, does everybody understand what we do? We take the least significant bit of A and the least significant bit of B. So that's A0 and B0, and feed them into a what? What is this?
half adder.
A half adder. Of course, inside this is a what? Inside this half adder is what? 1, and one exclusive or and one and, right? Is everybody with me? And then that sum is S0, the sum of the result. But then the carry out of that half adder goes to the what? To the carry in of the next stage. And then we add A1 and B1, the next bits of the two numbers. And then that sum is that, and this C out, and et cetera, et cetera, et cetera. Now, does that make sense? Are we good? And then it ripples, so the carry ripples through. And so how would you know what the performance of this adder is? You'd have to go through and count the what? How many what? Gate delays from, the longest one from the input. It's the longest. And that's an exercise, by the way, you guys. I'm going to ask you to do that. Count. Yeah, question?
Yeah, for the V coming out with the XOR.
Yeah, that's a good question.
Say if you had like 6, like A1 through 6 or A0 through 6.
Yes.
Are the ones going into V still just those last two?
Yes, the answer is if there's more than just 4 bits, like if you have an 8-bit adder, the answer is, and the question is, how do you calculate the V bit? We need to think about that. And the V bit, the way you calculate the overflow is you have to detect what gets carried into the sign bit. And the sign bit is always the leftmost bit. Do you see what I mean? So the answer is yes. The V bit is always takes the carry. It always depends on the carry of the last one and the carry of the penultimate one. Are we good? Okay. And furthermore, let's think about that here, because what does this now? You see that C out, the C out of the whole thing is just the C out of the last stage. But what about the V? What about V? Why is this? What is V? How do we calculate V in the hardware? It's the exclusive OR of what? Of the C out and the what? The carry into the sign bit from the penultimate stage. Are you with me on that? Now the reason that works is here's how you compute the V bit. So you can only get an overflow in one of two cases. Either A and B are both positive and the result is negative, or A and B are both negative and the result is positive. Remember that rule? Well, that's those two cases. Are you with me? That's those two cases. So if you work it out, the way you calculate the overflow bit is with the exclusive OR on the last stage and the penultimate stage. All right? Now you guys, watch this. This is so cool. We're just learning all this digital logic design stuff. We can understand all these circuits. Now watch this. How do you suppose you subtract?
Flip the bits.
You add the negative, yeah.
Right.
But the way you subtract two numbers is so in order to do A minus B, instead of doing A plus B, suppose we want to do A minus B.
You do A plus negative B.
You do A plus negative B. Right. So now we have to remember the rule. Do you remember this from computer systems? How do you negate a number? Some of you guys are in computer systems now, actually. You just had it. Others of you, it might be a little bit of a stretch.
Is it one's complement or two's complement?
Well, you take the two's complement. And do you remember the rule for taking the two's complement? Here, maybe we should do it. Let's focus over here. Suppose we have a number like this. 0, 0, 1, 0, 0, 1, 1, 0. Suppose this is a 4-bit number. Now, what number is this? What number is, and let's suppose that this is the sign bit right here. So what number is this in using 2's complement binary representation for an 8-bit cell? What number is this? How do we do this? This is the, what place is this?
That's the 1.
1, so this is 2,
plus
4. So 2 plus 4.
Plus 32.
8, 16, 32, plus 32. So what's that?
38.
That's 38. So the question is, what's negative 38? Do you remember how to do negative 38? What do you do? Flip the bits. 1, 1, 0, 1, 1, 0, 0, 1, and then you have to add 1. Is everybody clear on this? So what is this?
This is
1, 1, 0, 1, 1,
0, 1, 0.
1, 0. Right? So this is this one is 38. This is negative 38. And how do we verify that it's negative 38? Do you remember the rule for verifying, for getting the magnitude of a negative number?
Add it back to itself.
Well, there was a way. Instead of looking at the ones places, do you remember how to do that? Instead of looking at the ones places, what do you look?
Look at the zero.
You look at the zeros places and add 1 to get the magnitude. Notice here that there's a 1 in the sign bit, right? So to verify that this is negative 38, you add the zeros places. So this is which place? This is 1
Plus 4.
plus 4
Plus
8, 16 plus 32, and then you have to add an extra 1. So this is, sure enough, this is 38, which means this is negative 38, which means this is negative 38. Right? All right, you guys, but look, are you ready for this? What we can do is, we don't want to have a separate adder and have a whole nother separate subtractor. What do we want to have?
It's just a subtractor. Oh.
No, we don't want to have a separate subtractor.
You want to use them as the same.
We want to have a what? And a what? No, we don't want to have a separate adder and a separate subtractor and do, because how do you subtract?
You add the negative.
You add the negative. So we want to use the same circuitry in the adder for adding the negative. Do you see what I mean? We don't want to have a separate adder to add the negative.
Right.
We don't want to have a separate adder and subtract. We want to have one circuit that does it all.
So you just invert it and add 1.
So what we're going to do is we're going to have a control line that says, and that control line is going to come in, and that control line is going to say whether or not we're adding, or subtracting. Are you with me? Now, if we're adding, then all we have to do is what? Now think about this. This is so neat. If we're adding, all we have to do is take what? A and B and just add them.
Yeah, just the way we
Just the way we just did.
Right.
But if we're going to subtract, what do we need to do? What do we have to do with B? If we do A minus, what do we have to do?
Or negate it.
We have to negate it. Well, wait a minute. How are we going to negate it? How will we know whether to negate it or not? We will use a what?
An invert.
A what? No, a what?
A selective inverter.
A selective. The control line will go to our selective inverters. And if our control line is 1, that means we're going to subtract. And when B goes through those XOR gates, it'll be inverted.
Right.
Do you see what I mean? But if the control line is 0, then it won't be inverted, and we'll just be adding.
Right.
Do you see the idea? You see the idea there?
So when the selective inverter is 1, will there also be a way to carry that 1?
Yeah, that's the other thing. What about that 1? What about adding that 1? Oh, that's a great question. Now, can you think about how to do this? We can almost design this in our head.
You have to carry. You would carry that same 1 from the selective inverter through and add, or if it was a 0, you would add it to.
It doesn't make any difference if we add 0
Right, exactly.
when we're adding.
So you just add it as well.
So we take that control line and we just put a full adder on the right hand side, and we use we have the control line go into the carry in.
That makes adding take twice as long every time.
No, it doesn't make it take twice as long. It's one more gate delay.
It'd be a full gate.
It was one more gate, one more.
It doesn't have to add.
Yeah, no, but no. If you add how many gate delays for the whole thing, it doesn't double that time. It's just one more stage. It's one more gate delay. It adds one more gate. Because see, the performance, yeah, it's going to be a homework exercise to calculate the performance in number of gate delays. And it won't be, depending on how long, and you guys see that depending on how long the number is, like if it's a 32-bit number, it's got to go through all those gates. Are you with me? Okay, so look, you guys, here it is. It's based on the relation, so the adder subtractor, so this is going to be an adder subtractor. It's based on the relation neg x, the negation of x, equals 1 plus not x. And furthermore, the XOR gates act as a selective inverter. So the way we do a minus b is we do a plus the negative b, a plus neg b. And here it is, you guys. And we can understand this whole thing. Man, check this out. You got to be impressed, right? How easy it is for us to do this now that we know all of this combinational circuit techniques. Look at this. The only difference look at figure 10.53a. In part A, what's the only difference between this block diagram and the block diagram we had for just the adder? The only thing we have different is what? No, in the top, in the block diagram. I'm not asking about the details. The only difference we have in this block diagram is a control line coming in from the left that we call what? Sub. So, this control line called sub, if sub is 0, what are we doing? We're adding, and if sub is 1, what are we doing? Subtracting. And here is the block diagram. Sorry, not the block diagram. Here's the implementation. And look, let's consider in part B, figure 10.53b. Look, let's consider what happens if sub is 0.
Oh, so they do the addition before
If
the inverting.
sub, well, let's just consider the two cases. If sub is 0, then the left-hand side of each one of these exclusive ORs is what? Is 0. Which means what's happening to B? Which means what's happening to B? I know, but if the subline is 0, like if then what happens to B when it goes through that XOR gate? No, it's not flipped. It stays the same. Are you with me?
Yes.
Is everybody clear on that? If the subline is 0, then there's a 0 coming into the left-hand side of each one of these exclusive OR gates, and what that does is that's a selective inverter. So what happens? B just does what? It goes through unchanged. Are you with me? It goes through unchanged. Does everybody see the principle? This is principle of operations. And when you do the lab, you're going to do lots of principles of operation to understand how the principles behind how the operation works. Are you with me? Are we good? These are the principles of operation of a digital circuit. Right? And furthermore, if sub is 0, what is going into the Cin of the least significant full adder? 0. So in that case, what is the least significant full adder doing? It's just adding what? A plus B. And there's no carry-in, and the carry-in is 0.
So do they use?
Hold on. Let me finish. Did you have a quick question before?
Yeah, does that mean we don't even use half adders?
In this implementation, right. If we're going to have an adder subtractor, we don't even use a half adder, right. Okay. And now let's take a look at the scenario when sub is 1. If sub is 1, then the left-hand input of each one of these exclusive ORs is what? Is 1.
Right.
But since the exclusive OR is a selective inverter, what does that mean? As the B's are going through, they come out what? Inverted, flipped. And not only that, but because sub is tied to the Cin of the least significant one, we're doing what? Adding an extra what? 1. Which is what we need to do to take the negation. And so what are we doing? We're adding A plus negative B. And there, everything else is the same. Ha! Yeah, question?
So do they use adder subtractors, like
Inside
half adders ever used except for within full adders?
right. Right, yes.
They are?
Oh, no, no, no. What you said, they are used inside full, yeah.
And that's it.
Yeah, that, well, you know, you can have specialized, I mean, you can't say never. Don't, never say never, never say never. I mean, there are probably some specialized applications with some control circuitry where you need to do a half add, you know.
Okay.
But anyway, but we know the principles and we know how to do it. Now, does everybody see how this works? Excellente, good deal. See you in the lab tomorrow.